So thank you for letting me in the chat that you cannot hear me. So now you should be able to hear me, hopefully. So I thank you for letting me to do these sessions in English. It just will help me to also share the same material to English people, to the students, international students as well, and some other colleagues. So thank you for that. And if you have any questions in Latvian, you can surely write them in the chat or directly to me in other communication channels. So just to double check, so can you see and hear now? So can you see? Okay, now. So plus, minus, let me know if there's any other problems with connection or otherwise. Okay, good. Then let's do another question around here. So how many of you have worked with me or done a course with me before? So plus, minus, just need to double check that especially the students who get graded for this course are familiar with the process and also with the way how we organized either live or in-person sessions. So normally in live sessions, if there is no in-person class, we're communicating to the YouTube chat primarily. You can also use tools like, for example, Gist or Pastebin to share code with me. So you can quickly copy some code and share with me so I can help in a live session to debug your code immediately. So that's one way to communicate. Okay, I see that probably all of the students are the same ones which worked with me in previous courses, and I see also Matis, so that's great. Yeah, so the idea will be that the materials and the homeworks, everything will happen in Google Classroom. Then we will communicate in YouTube chat. If this would happen in person, which would be great, then we would communicate through Google Classroom, but now it's primarily to the YouTube chat here. And also, what else? Yeah, so the grading, so the mark for the course, it's 50% the classwork and 50% of the homeworks. So 50% of the classwork, 50% homeworks. It's based on the scores in the Google Classroom. You will see that as well later on. And we will check time to time what is our current situation. So that's about the grading and the course material. Or maybe I should also point out that we also have it listed in the Google Classroom itself. But in general, the plan for this course is something that is my research interest as well. And so there's these materials. Let me show you. So we'll start with Siamese networks or contrastive loss, and I'll explain also a bit like why it's important and how more powerful these models are than others. Then we're going to work with sampling methods. So what I mean by that is that normally you have batches, right, in random order for the training purposes. So I assume, at least from the chat, that all of you at least have basic knowledge on the intro course or working with me previously. So normally you have like just batches from the random batches from the trained dataset, but there is other methods as well which are sometimes much better. So you can prioritize your samples in batches and order them in specific ways to get a higher like results or faster convergence. Then triplet loss, which is also quite a powerful technique from which a lot of other techniques emerged. Then proxy NCA loss, which is very interesting in the sense that we don't need, in one version of that, we don't need a number of classes in the data set. So it's really cool technique. And all of these first four, and actually also the variational autoencoder here, they are field which is called deep metric learning. That's why this course is also DML. So DML, or there are actually an alternative way to saying that I will also write down. So you can find that on scientific literature, deep metric learning, and also it's called distance metric learning. Yeah, so the easiest, the kind of like the most easiest ways how to do that, and we also will use that in our course, is some kind of dimension reduction techniques, like for example principal component analysis, or there is also non-linear principal component analysis. There are some few other like the NCA itself basically is something that also could be used for dimension reduction. Of course, SNE. So there are quite a few really powerful techniques which are kind of like fitted for the current data set to extract these metrics. So the keyword here is the metric, kind of like embedding or metric, basically. Yeah. So the metric is also something that we will discuss a lot. So okay, so we will return to this. I know this might be confusing in the very beginning. I will return to this in a second. So that is regarding the metric learning. This is also useful for 0-shot, 1-shot, k-shot. Then there is a few sessions where we will look at these embeddings, basically, that you can use these embeddings for generative models to generate back something meaningful, and especially for generative models, the cleanliness and the orderliness of the metrics is very important. So that will be really interesting. So these will be, again, generative adversarial network type of models where you would generate out the new output from the input. And the last one could also be used as a style transfer, probably, but it's also basically more in the generative aspect, but it could be also used as a style transfer. For example, if you have some input of image, like change the so you have a picture, for example, and then you get out the like artwork style or something like that. So all of these are quite powerful techniques, and we'll discuss them one by one. And just to return back to these metric things that I was starting to confuse you. So the idea here, let's go actually to the first slide, so is to use some kind of model that could extract the embeddings. So there is some kind of encoder, like ResNet, DenseNet, or any convolutional encoder. It could be like also for the classification purposes, that kind of encoder. We're gonna actually, the first task we'll do today is just to remind you how to build these classifiers, and then try to change it into Siamese network. So there is some kind of convolutional encoder here, and it generates these embeddings. These embeddings, like if that would be a classifier, this would be a logit that you would pass to the softmax, and then generate the just the class distribution, probability distribution. In this case, if you're talking about distance metric learning, basically the important thing is this embedding and then how they relate to each other. So here we have two different input pictures, right? The samples from two different persons, and what we want actually to have is that this embedding has a like distance between this embedding, and if I have more samples of this guy, they will be all clustered together in the same place. And it could be done in some manner just with the classification models, but it will not be as good. So I will explain that step by step more and more. And if you have any questions regarding so far what we're discussing, then please type in the chat. Feel free to type also in Latvian. Just try to explain more in detail all of this this material. So again, just to emphasize what is happening here. So here, the idea is that there are two kind of very important terms, basically maybe three terms. So first of all, we have the embeddings. So the embeddings are these latent vectors z, which are should group by X class, or just basically by the Y class for each X sample. So the X sample in this case is an image. It could be anything else. It can be the voice print, you know, like audio sample. It could be image. It could be like sensor data. There are a lot of things that it could be. So, and the Z vector, which is the embedding, should cluster basically, by the Y class label, by Y class label for each sample X, right? So that's one. Then the other thing is the distance, or the metric basically. So this is some kind of measurement between Z's. So that's why it's called distance metric learning or deep metric learning. So the metric part. So here in this case, the metric is so it could be L2 or cosine. So this kind of mathematical notation normally just means any kind of distance metric, but in generally what you would use is either the L2, L1, cosine, or some other, like there are a few other metrics we could use. And so the idea is now you have some samples here. I think this is a CFAR dataset, CFAR 10 or something, where there is like a lot of like pictures of different classes. So here there is, I think, the horse class. Which one was the horse? I think these were the horses, and these were the deers, I think. So they are quite similar in the appearance, right? And then some horse, which maybe is mislabeled or just too similar to deers, is appearing in that cluster. And what we are trying to do is to push away all of these samples which are not belonging to this cluster with some kind of margin from this cluster, and pull in all of the green ones. So if some of the green ones is here, I want to pull them into this cluster basically. And the way how we do it is by using these very specific loss functions and the metrics as well. So right now the metric is just L2 distance or L1 or cosine distance. So in cosine distance there is the so this will be from 0 till 2 the range, right? So but don't worry if it's still doesn't make fully sense. We'll go more and more in details. You will start getting the picture. Just don't worry if it seems a little bit confusing yet. So again, dimension reduction techniques are quite necessary to analyze these kind of metric models. Remember, I said that like the very simplest approaches for kind of distance metric learning is any of the dimension reduction techniques, but they directly as such are quite not as useful for the models itself. So I mean, if you would just feed into the principal component analysis, which the main task for PCA is to keep the the largest standard deviation projected on the axis that you provide. So if the idea is if I would pass in here, let's say that now, so we will work with some kind of images. So 28 by 28. So these will be these. Later we will gonna work with more interesting data sets. But so in the beginning, this is just grayscale image of a letter like A, B, C, D, E, F, G, and so on. If I pass it to the PCA algorithm, this kind of dimension reduction method, then there is absolutely no problems of getting out any kind of like two-dimensional or three-dimensional or four-dimensional data point that is kind of representing that image. And then I can use some kind of clustering algorithm like k-means or spectral clustering or any other to classify those classes, and this would be like cool model. But the problem is that if you're just using without any kind of neural network type of or deep metric learning approach, is that this would be quite noisy, because this PCA is trying just to preserve all of these maximal standard deviations, but it's not actually extracting all of the any kind of like knowledge out of that data point, like the image. It's just doing very basic maths, and even though the output is the same as it would come from for example the Siamese neural network that we're going to use, or the kind of DML or something like that, any models, the output looks exactly the same, but the value of that vector at the end is much greater for any of the deep metric learning type of models. We're going to return to this again, definitely. So here there is again example of MNIST dataset. There are 10 letters, right? I think definitely those of you who worked with me or had the courses with me, you know already all of these datasets. MNIST, but then also the PCA. Maybe I should give some images more regarding that. So today we're also going to work with similar dataset to this, a little bit larger one, where there are like these images, grayscale images of letters, right? And if I'm doing this just as a classification model, right? So this will be the classification, which we will try in the beginning. First of all, we'll see that the embeddings from the logits, if I would project them using PCA, so the embeddings is actually 10-dimensional. Okay, so the logits or embeddings are shape in this case is 10-dimensional, because we have 10 types of numbers, right, which are classified from the image classifier using convolutional neural networks, right? Then we pass it to PCA, this dimension reduction algorithm, basically, and we get out the two-dimensional embeddings, which could be then displayed on this matplotlib graph. Maybe we could get also three-dimensional, which would also be possible to display, right? So just let me find, maybe I can give you some more example regarding the PCA, what it is, if you have not, if you're not super familiar with that. So, Okay, I'll just drop in some image. So this is really hard, I think, to present on just 2 dimensions, but there needs to be a little bit of imagination, basically. So, okay, I will go back here to the PCA slide. And by the way, there is really nice ways how to do this. We're using, I think, was it called kernel trick? Basically, mathematically, really nice ways how to do this. So if I have some data set, and in this case, this is tricky because actually what's happening here is 2-dimensional data set is then passed to PCA, and I get out again 2-dimensional data points, right? So that's why it's tricky. But normally, the input here can be really large number, like for example 32-dimensional to 2-dimensional. So if I have like 32 sensor data, like some robot with 32 sensors, then I can pass it to PCA and get out 2-dimensional representations, right? And the way how this works, this is so this will be a linear PCA. There is also a non-linear. So there would be the idea to find automatically, so there's this kind of like algorithm to find, so either it's iterative or it's just a kernel trick in just in one go. So to find these kind of axes, so the new axis where to project this data set, and the way how to find these 2 green axes, PCA1 and PCA2, is to preserve the most of the standard deviation. So you see that PCA axis 1, it has like very large range, right? And we want to get the number of axes which we define. I want to find two axes which are the best to preserve all of the variation in dataset. So this axis preserve the most variation, and then this axis preserve the most variation. That's why we choose those and we project all of these samples. So then what would happen is that we would project like, so this guy, for example, we would project on this axis here, and then we will plot it. So we could also define it, for example, we could define it from 32 to 1, which would not be a great way. But if we would project it to the 1 axis, then that would be only this largest axis, not the other one. And if we would project it to 3 axis, for example, then it would try to find the 3rd axis, which would probably be this one, somewhere like along this direction. So that's the idea of generating those projected reduced dimension embeddings using some established techniques like PCA, nonlinear PCA, TSNE, and so on. So many of them are actually also quite iterative, and really there's much more than that. So, but anyways, the idea is that now we learned with our model these 10 logits for the class distribution. Then we are passing them to the principal component analysis, getting 2-dimensional representations, which we can then nicely plot on the plots, right? I really hope that so far it's clear. You might have some problems with the full understanding, but at least like in some part, and when we will code it, you will definitely get it better. So you see, so there are a few problems already. So one problem is that just the raw outputs of these logits, they do not separate that well. So for example, we can see that number 1 separates really well, then others are really mixed together, right? And it's not something that is super useful for clustering techniques, right? Then if we apply some kind of normalization, it's also very common to apply all sorts of normalizations to the embeddings. So if this is some kind of unit embeddings, like L2 spherical space or something, then you would get a little better separation. And this would, maybe you would think this is really nice, right? The classification separated these embeddings quite nicely. But then arises some additional problem here. So what if the two clusters which are right by each other are not similar at all in their appearance or in their input feature types? So that is something which classification cannot really properly resolve. So for example, if we look at here, so this, I think this is really also not too bad example, hopefully. I did not study it yet in detail. So the 3-2 contrastive normed, let me check, 8, 5, 6, 0. Okay, I did not run these examples myself. We will run our samples and hopefully they will produce even more convincing results. So here the idea is that you see that what kind of numbers we have, what kind of classes we have by the types of letters, right? So this is letter 2, right? Okay, so I don't like that this color is not visible here. Well, okay, so this is letter 2. This is letter 1. So then, what is the red one? Letter 3. Oops. Letter 3. Then, so these are just like visual features, right? So what we would expect is somehow to try to arrange those visual features in some meaningful manner, so that later on, if we run these models, if you run these models for some actual production cases, we would like to have that those embeddings have higher value, so they smoothly go from similar images to another similar image. So that the idea is just like in the autoencoder, right? Or the variational autoencoder. Let me just remind you what I mean by that. Variational autoencoder. MNIST. Remember, we did the variational autoencoder in MNIST, and it actually did some meaningful separation of the embedding. So here there's again the example. So if we imagine that x and y axis are these two axes for the PCA 2 and PCA 1, then I mean, like if you have just not PCA, but if you have embedding, if you would have some kind of Z with shape of 2 dimensions, then this is what would be good to have. Oh, sorry, the color is white. So the Z shape, if this is a 2-dimensional shape, then this is what would be great. If the model would learn that smoothly, you would like transform from 7 to 9 to 4 to 5 to I don't know, like to 3 to 8 to what else there is, to 5, I guess, again here, then to 0. So it's like a smooth visual transformation. So in this case, visual, because the data is visual, right? So, but if the data would be actually some kind of I don't know, like sensor data, then also we would like to have like smooth transitions to each of the similar classes, right? And here with the classification models, we do not get that. With the classification models, there is no guarantee. Even though we have nice clusters, there is no guarantee that these clusters would be similar in their appearance when they are right by each other. It's possible that it might happen randomly, but there is no kind of enforced effort to make sure that it happens. So here, let me see, this is 6 class, then this is a 0 class, right? If I'm not mistaken. And then in let's see in the last image. So they say that this is a contrastive type of model. So we will do the same thing today. And in a contrastive type of model, depending on a lot of parameters, starting from the loss functions, the structure of loss function, also the what else there is, the sampling methods, the model itself. There is quite a few parameters, but if you fine-tune the parameters correctly, then what is expected is that the output, the visual features are kind of similar in the way how the autoencoders work, but they have much more control over it. It's not just like kind of like a completely unsupervised manner. So there are some elements which are unsupervised and some elements which are supervised. So here in this case, like just in a classic way, the contrastive loss and the Siamese networks, they are actually supervised method, but there are alternatives as well. So here, if the red one is 3, then what's similar to that, there is some kind of overlaps with all sorts of things, but not a great overlap, I guess. Then in the middle part here, maybe these are more similar. There's 8. So this is then 8, and then right by it there is the brown one, which is kind of 5, and then again the PCA, depending on the dimensionality, also I'm not totally sure that this result is what we want, but anyways, so 2, 1. So I see that 1 and 7 is together, so that's good, and it's actually the same also in the classification model. 1, 7. Maybe I can find some example here which would be different from classification model. So there in the bottom part 9. I will check chat also in a second. Maybe you can find some sample here. So 9. At least I'm trying to illustrate the idea. So 9 and 4 is together, so that's really nice. And here the 9 was the blue one, and the violet one. Yeah, so you see there's already one pair which is a little bit more different in the classification and the contrastive example, at least in which this one. I should definitely make my own sample for this image for the next time. So let me show you. So these two here are separated by the 7 here in the middle part, and here they are both together, for example. So and in the classification model, there is no actually kind of there's no enforcement that similar type of features should cluster together. There again, this can happen randomly, but it's just not something that you enforce. And yeah, and also like because the way how the classification then works, this last layer of the softmax and the probability distribution, there's really no kind of incentive to move them closer to each other. So I hope this makes sense so far. So let me ask in chat in the question. So do you understood difference between classification models and deep metric learning models with regards to embeddings? So just a second. Plus minus, if something is not clear regarding these few things that we already discussed, let me know in the chat. If everything is not clear, then you, I don't know, like type in minus but it will be really good if you can try to point me in some direction where I can explain more, and then we will look at a few other things, and then we will start coding these things. So are you all asleep? Or maybe I already talked too much. Oh, there's again, but it's the same also here. The 0 and 6 is together. 0 and 6 is together. So what I'm trying to say again is that classification models, the embeddings or logits, generate some kind of like clusters, right? Which could be distributed evenly in the space that kind of resembles the similarity, right? But there is no specific mechanism to enforce their similarity in the embedding space. But the DML, yeah, okay, thank you. I see in the chat that the third graph we could explain more. But in DML models, there is a mechanism to try to move those embedding clusters closer by the difference. Yeah, DML has control over the way how these groups, these clusters move in the space. So I see the question in the chat. Yes, so one of the big differences is that we have actually mechanism how we can control what is the distance between these clusters is in separation with each other, like the distance between these two guys, so like with this one, like so we don't control exactly the position in the space, so that the trees should be somewhere here, but basically we control the relative distances between them, and these the way how, because we control these relative distances, the kind of similarity between the actual semantic knowledge, so something which is inside these things, or the visual similarity, or any other kind of meaningful similarity could be better encoded in these kind of models. So, but the way how we project on 2 dimensions using PCA. Using PCA, we project these large high-dimensional embeddings is exactly the same for all 3. So the PCA is just like a small tool that we can use to reduce dimensions from 10 to 2, so we can visually see them. If we have only 10-dimensional representation, we don't have 10-dimensional matplotlib, you know. That's why there is this term PCA and this algorithm. Okay, so that's about this far. Then why this matters, I hope that I will manage to explain why this is really cool type of model. So we'll try to find even more images. So the idea is here that what we're going to do also today is that the training data set is different from test data set, but not in the way that it's 80-20% split, but the classes in the training data set are not the same classes as in the test data set. So training data set contains, for example, the training Y classes are for example the let's say A, B, C, and so on. So some kind of letters and numbers, right? And then for the test inference phase, we can even see in this image there is the O or 0 or something like that. O, then what else? There is the L, then the K. I think there is the M. So, and these O, L, K, M, they are not included in the training data set. So you immediately already see some problems here. So how then you can train the classifier if you have different classes here and different classes here? It's like it's not possible really. So even if you train it using the classifier on the training phase, which we will try out today as well, and then apply it on the inference, different samples, inputs, the output will never look something like this, you know, like it might look similarly, but it will never be as good separated as using some kind of DML methods. So, and so one is that it's possible to do, if this is the case, then this is called zero-shot learning. So zero-shot learning. So when there is absolutely no overlap between training and test classes, right? There is also a possibility to do like a one-shot, a k-shot learning, one-shot or a k-shot. So in that case, it just means that one sample of O's, for example, can be included in the training data set, just one sample. Or k-shot, it might say, like, let's take 5 samples of these and include also in the training set. But in general, like in most cases in real-life solutions, you would probably use zero-shot learning. For example, if you have the situation when you want to create the Face ID model, for example, that is actually used probably in Apple as well, in the you know, like Apple Face ID. Let me try to find some more images. So in Apple Face ID, of course, the model which is used, which also uses the depth camera and images processing and everything. So that model is not retrained every time when you enroll your own face. So it's like we don't know exactly how like in very detail how it works, but it's very unlikely that they retrain that model every time when you enroll in the system, right? Instead, you have one pre-trained model that is only pre-trained once, and then this pre-trained model just would cluster your face features together in this one cluster, and this cluster then would be possible to separate from all other faces. And the idea is then there's even more cool things that you can do. First, you can like find some outliners, clean up your data. Like if you, for example, was doing Apple Face ID enrollment and then for one moment turn away, you know, like there's a very bad data sample, and this data sample would jump out of your cluster. You can clean it up, and then afterwards you can also decide on what kind of metric you want to use. Like what will be the, like, is it like a center of the mass and then just L2 distance, or you want to check each sample with regards to any other sample, right? There are quite a few ways how to approach this this situation. So let me see if I have some animation here. If not, it's okay. Yeah, so this is really powerful way how to basically make this useful. Okay, unfortunately, I had a GIF animation, but it's not working here. But after you train some kind of model, like in this case, this is a VGG phase 2, then using any kind of deep metric learning, you can drop in your face and it will cluster together, and you can separate it without retraining model. Of course, you can do the same thing with almost any other type of data, you know. And then just this last missing piece before we move on is how then we classify them, how to classify these novel classes, novel new classes. So there are few methods. So one is clustering. So, and then you can use k-means or the spectral, or there's a lot of methods. So after you do the clustering, then you check, okay, in this cluster I have my enrollment samples, so this means this is me, right? So this is one option. Then another option is just using your own samples as anchors, and then use some kind of distance metric. So anchors plus distance metric. And of course, some of the distance metrics are L1, L2, cosine. Cosine distance, you can imagine, it's like an angle between those two vectors, right? So let me quickly find, I always misspell that some other distance metrics which I know from top of the head. So there is also another option to use Mahalanobis distance. So idea is that with that one, that basically it's almost the same as if you would apply the PCA whitening before the L2 or L1, and then get the distance metric. But with this one, it's kind of like the whitening, or trying to center all of the, trying to preserve the variance and reduce the kind of noise. Is included in that distance, but there are quite other. So there's also like PLDA. So this one was used before the deep metric learning. From deep learning, it's really powerful a way also to measure kind of similarities between the metrics. So basically, this is the way how then you classify those samples. So let me check in the chat if this part is clear, and then we hopefully will start moving towards the code. So is the classification of new classes in the clear? Plus minus. If something is not clear, let me know. Again, the thing to remember is that I'm talking about the classes which were not included in the training dataset. So you see that you have a lot of things you can do after you train the model and without retraining it. Yeah. So, okay, yeah, I have actually the results somewhere. Let me think. Where did I have the results regarding the one shot and the K shot and zero shot? There were a few publications which I am aware of. Let me quickly try to find it. If you have so far you can answer in the chat. This is clear? If you have some questions, we'll try to find. Where did I had it? I definitely had it somewhere. There are quite a few publications regarding the powerful effects of having deep metric learning incorporated for the classification task, in the sense that you need a lot less samples. So I mean, if you're just including one shot learning, right? Then imagine like if you would do the simple classifier, it would give you quite bad results. You know, like even if you apply the weights, right? If you apply the weights to the cross entropy, it will still give you really bad results if you have just one sample, right? But if you're using the deep metric learning, then just this one sample can give you really good results. So that is one of the reasons why this is really powerful. But I'm trying to find where did I had it? I have in my mind one chart really nice from one publication, but which I cannot find anymore. Anyways, so I will try to find that chart for later. But just to reply to that question regarding the why one end shot or why or end shot is better than zero shot, or why would you use it, is that if you would use just the cross entropy, right, then you apply weights to the imbalance of the classes, right? So the best weight models would train if all samples of the classes have the same count, right? If I have like hundreds of these, hundreds of these, hundreds of these, and so on. And then if I have just one class with one sample, or 3 samples, or 5 samples, then I would apply weights. So I would say that please do higher loss for those samples so that they would separate better. But at the same time, if I would try to do that for the classification model, the results would be quite poor, actually. Like, I don't know, like the accuracy would be like, I don't know, like maybe definitely not 90% or something like that. That also depends on the number of other samples, right? And the complexity and the noisiness. But then if I would just include, if I would do the same experiment with 1 or 5 samples using the deep metric learning, where they are included in the training set, then I would get the accuracy above 90%. So they would be much, much higher accuracy. I will try to find that image maybe sometime either today or later from the publication. That is really good question. So why to use one shot or the N or K shot? And the simplest answer is just that the classic classification do bad with this, but in real life problems you often have this kind of situation, and then you would apply deep metric learning. So okay, so that's far so good. And then let's look at the next part. So then what we actually are doing here is we are getting those Z embeddings, right? So let me find where was this initial image. I promise you that we're going to start coding it very soon. So here these embeddings, those will be the Z embeddings, yeah. So there's a Z, and here will also be the Z, and in this case there will be so this will be ZA. So we'll have one target class, and then if this is the same pair or not the same pair. So in this case, this person is not the same person as this person, so it means that this Z will be negative Z. If this person is the same with this person, this will be Z positive. So it depends only on the information regarding the input class, for example. And afterwards we know if this is like with regards to every ZA, if this is a ZN or ZP, if this is a positive sample or negative sample pair, then in that case we can calculate for the loss function these metrics, so the distances basically. So here there will be the positive distance. So for every pair that we have the same person in like where the ZA and Z here is the same person, then we get this distance. So and for every pair where this is a negative pair, where the classes do not match, right? Where the classes do not match, we get the N, right? So and in this case, we could think that this is a pairwise distance just L2, or again, this notation in publications often used in very different ways. So it means just some kind of distance. So we have the distances between positive and negative pairs, and then we have the loss function, which is then this contrastive loss function, which is very old loss function. I think Jan LeCun invented it in early 90s, so it's really old but very powerful. So basically, what we are saying here with this loss function is a very simple thing. Again, this notation very often shown in publications, but it's actually what it is just the max of so max m minus dp comma 0. So that is what it means, okay? And just maybe I should explain, so that this means, so this could be, if this is an L2, then this is just like ZA minus ZP squared, right? So anyways, so this first term says please bring all of the same class samples together in the embedding space. Try to make them as one cluster, right? Often there's also some kind of additional term to avoid that they collapse just in one point in the space, so that's also not optimal. And then this other part says that push away all of the samples so that they would be at least this margin apart. So the margin again is also hyperparameter. So it says that depending on your space, so in this case, if this is an L2 spherical space, so then the distance can be in a range from 0 till 2. It varies depending on your embedding space. There are different kinds of distance spaces, you know, like for L1 it will be different. So and then I would say if this is my range, then maybe it would be a good hyperparameter to try out that the difference between the margin between clusters is 0.2 or maybe 0.5. And it says that please push away all of these negative pairs to each other with this kind of margin. And then they will start float in this embedding space. So in the beginning, everything will be random. Then they will start to come together to the same point. And then they will start to like being pushed away slowly. So that's the idea. Maybe I can quickly find some image for that. Just a second. We also will have quite nice illustrations for our today's practical work and also for the homework. At least I try to do that. Okay, I see something that could be useful, hopefully. Yeah, so let me show you. So here, this is the idea. So if I have some kind of, so the yellow classes is the anchor. So the anchor is the middle one, and then so the colors are different classes, but basically the anchor here is the middle one, and then it starts to pull in all of the samples which are the same class, right? So this is after the training cycle, right? And then all of these colorful, like blue and red ones, are different classes, so different kind of personalities or any other types of data, and they are pushed out of this range. But not only they are pushed out of this cluster, but they also have this margin here. So the margin is what we are trying to enforce here. Yep. So I think hopefully this is clear. Let me ask in the chat. So is the loss function clear? Plus, minus? So meanwhile, I will try to open the first task for today. Okay, I see 3 pluses coming in. That's excellent. So I think yeah, we're very happy to see some very smart people joining in the course. I remember from last year, and I also know some I have worked with, so that's good. Okay, so I'm opening now the task 1.2. It will have a template with it. So you should download the template. This will be 500 points because the other one will be then the contrastive loss task, and then we'll have the homework. So 1.2 task is open. Okay, I see some question here. Nice. Loss function makes the distance samples different from getting distance of the samples different, getting them in a closer neighborhood, therefore making the clusters. Yeah, so the loss function, yes, is do not have like a global center, middle point, center of the mass for the cluster. Actually, the loss function do not know anything about the cluster. It just pushes them together and it naturally creates the clusters. There are a lot of other things you can do to improve that clustering process during the training, but like just in a very basic way for the contrastive loss, it do not actually kind of directly enforce like center of the mass of the cluster. So every time when I run this, if the next epoch, if the next batch, for example, this sample is the anchor, then all of these other samples would be drawn closer to this sample. So they are constantly floating. So it's not like just they are collapsing to one point immediately. So they will be next time getting closer to this guy, next time this one, and so on. So everything is kind of floating in this embedding space, and they are avoiding each other by the margin. So that is the idea here. Okay. So I hope this is clear. So let me ask in the chat now, is template ready for work? Plus minus if you have any problem. There is also also please get ready the Google Colab if you don't have GPU on your computer. Okay. So now I'm going to share the code, and we'll do the first together the classification task. We'll hopefully we will get a long way some interesting stuff. Really happy that you're engaging in the chat and trying to understand all of this stuff, not just trying to sit along and then code and then do not understand how to do the homework. So that would be not great. So anyways, let me go through the code as well. Okay, first I will wait for the confirmation that you have the code ready to work, and then I will explain the code. Great, I see the template is ready. So let's go over it. So in the top part here, we have few settings. So like if I don't have CUDA, then I don't want this to be a huge data set. So I'm saying that the max length per each class, so how many samples for each class will be only 100. You could also define that here for if you have CUDA, maybe to not have like tens of thousands, but let's play like few thousands, so that you can here define, right? So if you define 0, that means include everything. So 0 means include all, right? So that's here. Then how many classes should I include in the training, right? And testing. So I will split this to be probably 2 test classes and 8 training classes. And again, this will be random, but with a fixed seed. So every time I run it, it will be the same splitting of the classes. Maybe it would be so in total there are 62 classes, but that's really a large number. Maybe it would be good to reduce it also for the production. Maybe I don't know, like I will just leave it as maybe it's 20 or something. So I'm not sure that this is the best one. So you can play around with this. So it's just because the plots are very small. It's no problem of working with 62 classes or actually like in the VGG dataset where there's like tens of thousands. So it's just that here it's not that optimal to see. So then there is a emNIST dataset, which is like mNIST dataset, those numbers, but this is extended mNIST where we have letters also included. So that is what is this. Then we have splitting of the dataset not by the percentage of the samples, but by the labels. So I take all of my labels and I split them in 80-20%, just for the for one set will contain like A, B, C, D, and the other set will contain Z, X, Y, which is not included in the A, B, C, D, for example. So that's here. Then I have a small code which could be probably done once and then saved, but this is just like showing you how it works. It's accumulating the class indexes, so that at which point is which class, right? And then I creating the torch subset, which is from the full dataset just selected out those indexes which are interesting to us, right? Then here there is the I think only interesting thing here is the drop last, where normally actually what you would do if you have batch norm in your models, you would write something like this. So if you have batch norm in your models, you would probably write something like this, where you say that if I have last batch just containing one sample, I do not want this to be included because otherwise my batch norm will crash. So that's usually everybody is doing. But okay, what is this? I didn't get it why it's jumped over to some place. Anyways, so here, but in this case I have 12 because in the matplotlib I have 12 samples which I display as pictures, and if I have less than 12 samples for the last batch, it will also crash. Actually, for the training dataset, maybe it's not that necessary. For training dataset, I believe that here I can actually leave it as this. For the test dataset, it's very important to have it like that. Then we have a model, and initially we were going to build the classification model. Okay, so there is some kind of encoder. We could also use pre-trained encoder. For example, something from Torch Vision models, like Torch Vision ResNet or DenseNet or or I think there's also a few other efficient net, inception net. So we can use any of those as well, or we can build our own model. And then the last one is just a fully connected projection from 32-dimensional embedding, which would be one type of embedding which we could try out. Maybe we should use even smaller embedding because there is really not so many classes. But basically that's what we could do. Then I added here dummy code, so you can make a dummy code so that this class for classification works for you. Then here there is the loss function, where you just implement the categorical cross entropy. And here you have y index here, which you should select from the UI. I will just a second show you how to do that. Then calculate the accuracy, and then you get the results. So the results part, don't worry about these plots. I hope there is no bugs, but basically it should just show you the for the training set the accuracy and the loss, and then the separation also in the embedding space for the test set, and also some samples from the test set, which is not correct. I just realized that the test set do not include those classes. Haha. So let me think. The quickest hack for that will be following. So if you leave here, as it was in the beginning, lower than 12, so that will be fine. And the next hack we could do here is probably we can swap around the train and test dataset, but let's do that later. So if we just would swap them around, the first iteration would give us nonsense, but at least the classes which will be displayed in the plot will be the correct ones. So we can do that hack later, but by the way, this is just important for the classification model. For contrastive model, we could leave it as it is. Okay, so again, just to verify what we need to do. So the model to encode this, so the picture is grayscale, so 12828, right? To encode this to basically something like 32-dimensional. So this would be then 32-dimensional. Then at the end, what we need is something which is probably, so that it would work. It would not be perfect, but it would work better now to not separate different class probabilities for each of the train and test set. So we would use classes probably. So was it classes? Sorry, labels. Sorry for scrolling. Labels. So len labels. So this is what is our target shape. So depending on how many labels we include. And of course there is a softmax right? And then here there is the loss function, which is categorical cross entropy, right? And then there is accuracy calculation. Okay. So my question in the chat is, should I show you how to do classification model, or you will try to do this yourself? So plus is yourself, minus here is please show. So let's do a quick voting in the chat. So plus would mean that you will try to do this yourself first, and then if there's some problems, I will help you out, and we will see who can do this the best, the fastest. Or minus, then I will just start showing you how to do basic classification model from very beginning to refresh your memory if somebody is not working with deep learning that much. So 1 vote for showing. Okay, I assume that I should show them. It's interesting that some smart people are trying to avoid answering the questions to see that minuses accumulate so that I would show stuff. Even smarter would be probably to add plus when you see that there's a lot of minuses, so that you would say, I can't do this, but actually I will not have to do this, right? So anyway, let's start with encoder, right? So with regards to encoder, we can use kind of more modern approach, which is that the convolutions do not change the size of the feature maps, but just some other pooling operation does. So torch and then conv2d kernel, so there will be the input size in channels, which is 1, of course. The out channels is something that we define ourselves. So let's say this will be then, let's start by, like 4. Then kernel size, which will be 3, padding, which will be 1, or it doesn't matter actually, stride 1. So this is a classic combination where so what will happen here after the first convolution will be that the output, so if you add also batch here, so the output will be, after the first convolution, will be like that. Just the channel count changes, but the size of the feature map, width and height do not change using this configuration of kernel, padding, and stride. There is a formula for that. I showed that in the previous course, and it shouldn't be hard to find that. So that is this part. Then what could be do the next thing is to use the torch, and then so we could use some kind of normalization method. We could use group norm. So group norm is quite popular. There is reasons for it. For example, if you would have some kind of colorful images where some items are like in specific types of colors, and like if you have RGB channels and then there's just like some red balls, then maybe you would like to normalize the red balls together and the all other items together. And then if you have just like 2 groups of normalization, which are learned automatically, by the way, it would be better than just have 1 group of all of this, or using the batch norm over the channels. So that's really interesting method, which I also have been talking already previously. So here, let's see. So this will be then group norm, the parameters for group norm, num of groups and num of channels. Num of groups, num of channels. So num groups will be then, so in this case, the num groups should be dividable by the channels. So num channels, yes, 4. Then we should use some kind of non-linearity. The simplest one is ReLU, right? The leaky ReLU is a little bit better because there is a slope to avoid dead neurons, because everything that gets into minus will never get out from the minus, because the derivative from the minus part is 0 always. So what would be better is something called, for example, MISH. if you look at mesh activation function or swish or any, like what else there is, like elu, relu, algelu, all sorts of those guys, they are kind of continuously derivable functions, which are better in some sense than just something where it flips in the relu in very middle. But in the same time, it's not a huge difference. So if you would use relu here, the results would be quite similar. So it's not like a huge difference actually. So that's one part. Then we could use the reduction of the size of the image, which would be used then using some kind of pooling method. And I like to use upscale. So if I go inside the upscale, it's actually not upscale. It's really bad that they call this upscale. So because inside there, this is a torch F and an F interpolate, which means that I can interpolate it either bilinearly or nearest neighbor method, or trilinearly or bicubic, just like in Photoshop, you know, like just to reduce the size of an image or increase the size of the image. So that is the upscale. So there I can use the size. I think it was the argument size. Yes, size. So now I want to reduce the image size to something smaller. Let's say 2 times smaller. Hopefully this will work good. I'm not sure. So anyway, so this will be 2 times smaller. Then again, the same block. Maybe this same block could be as a separate class, torsion and module. That would be better probably. So here 4 to 8. Then again here we can have 8, and here we can have, let's say, 7. Then the next one will be from 8 to 16. So 16 channels. Now we could have 4 groups if we want. Again, these are all hyperparameters. I mean, like there is no perfect answer for this. What is the best answer, best combination, you know? So that will be this. Then at the end, we could have from 16 to 32 channels. 32 groups 4 mesh. Scale down to 1, and then we could apply just one convolution at the end probably. 32. By the way, now the kernel says size 3. It doesn't make sense. Actually, it also doesn't make sense here. So maybe I should leave it as 4. And here we could set it as 1. Kernel size 1, padding 0. I guess it doesn't matter actually here. I think, yeah, no, it will matter, but I hope that this formula is okay. I can double check it. We could actually double check it quickly. So where was my formula? So to have it like, so what will be the output is VOUT is equals as VIN plus 2 times padding minus kernel divided by stride plus 1. In this case, if this is 1, then just one double check that I don't have bug here. 1, 0, 1, 1. So kernel 1. Okay, this is not good. Stride 1, kernel 1. I think I had padding 1. I guess I need. Should be pointwise stuff. Okay, maybe I could stride 0. I don't know. Like, Yeah, I should probably set the stride 0. Okay, anyways, I think this way it will work. Okay, I actually just leave out this, but okay, no, let's keep it there. I will I will look at quickly at ResNet code. I kind of like just dropped out of my mind. What was the configuration for pointwise skip connection type of stuff? So this is one padding. Mm-hmm. 111. Okay, let's leave out it. I don't want to spend time on this. So you could make a just one by one convolution at the end here. It's absolutely no problem. It's just that I don't want to debug here. So okay, so we're reducing this down to size of batch by 32 by 1 by 1. So this is what we get here. Then the next thing is torch and n linear. So we will have to project it. So in features will be those 32 dimensional. Out features will be the number of classes. So this will be then the len of dataset full labels, like that. Okay. So this is a projection there, fine. So and then finally we could add nn softmax with a dimension of -1. Okay, hopefully this should work. So I will drop this to the Jamboard. And by the way, if any part of this code is not clear, let me know. So this is dropping to the Jamboard, slide number 8. Hope you can manage to deal with this. So then the the loss function. Okay, the loss function, maybe I should also drop to the Jamboard, explain a little bit more. Of course, you can use the built-in torch loss functions, but then you must be careful because don't add then softmax. If you will add softmax, you will have wrong model there. I definitely need then to explore in detail the equation for the built-in functions. So here, the categorical cross entropy, right? So in this form, this is a vectorial form, right? In vectors, where the y is the one hot encoded vector, and this is a probability distribution, right? You could also do the same exact thing using without using the y as a vector, but select y index from the y prim. So what I mean by that is, if you have like if you have like two vectors here, so let's say y, which will be the real class, right? So this will be 0, 0, 0, whatever. So and then the y prim will be something like 0.2, 0.5, 0.30. So and then then you would do the loss function here. Of course, one way is to multiply in pairwise those two vectors, but another smarter way would be just to select out this second term here, because this is not really super smart to multiply these two vectors together, just because we have vectorial form. We could just select out that item, right? So if we select out the index here, index 1, and we do this here basically, then we don't need actually the multiplier before the logarithm. So that is what we're gonna do here. So let me go back to this code. So to do this is then the minus torch logarithm, and here we go the y prim, which is the probability distribution of the classes in the train dataset. You see that we're actually only looking at that in the train part. If we would be in the test part, this would result in some kind of nonsense, because basically yeah, because these classes are not overlapping with each other, even though maybe the loss value would happen something, but it would not be correct. So here then this first part of equation can be written in this manner. So then we could select the y indexes like that. But then it's not enough just to select y indexes. We need to select from y indexes exactly the same, the index which is interested for us. So in this case, then we can use range of y indexes. I think in the other there were some kind of functions that does the same thing inside I think TensorFlow. I forgot the name of that function, unfortunately. E-8, like that. So. E-8 is just the epsilon for numerical stability, because of course the y prim could be 0 as well. And then logarithm from 0 will create us problems, right? So I hope this is correct. I did not check yet it. So I will try to run it later. And if there will be some problems, I will update this on the Jamboard. So on the Jamboard slide number 9, I'm dropping in the loss function. And then the accuracy calculation, which again is something you should be able to do quite easily. So this is just comparison of the indexes. We already have the index, the right index of the class, and also the right index of the predicted class, right? So what we do is we use the comparison here, and the output of this equation here would be actually something like true, false, and so on. But if I then multiply this equation by the 1.0, which means that in C type of languages, everything that is false is 0, and everything that is true is non-zero. In this case, this is 1 actually. So in this case, then we would get 1, 1, 0. And the last thing is needed to do is to calculate the average accuracy per batch. So then we would use the NP mean. So this will be the average accuracy of the batch, like that. And I hope this is it to make this able to run. And I hope we will see some interesting pictures now. So I'm dropping this to the Jamboard as well. And if you succeed by finishing this task, then you can submit it in 1.2 Google Classroom task, and so that you would complete the first task. So now it's splitting the dataset. If you run this code the first time, you will also download the dataset, which might take some while, unfortunately. So then this is a training part, testing part. Let me see what we get here. Yeah, we get this quite nice pictures. So basically, I will stop and explore more in detail, show you what actually this is. So on the top left part, we have the train loss and train accuracy. We do not have train test loss and test accuracy because the classes are different between train and test datasets, which then it will never actually get really good accuracy or actually also the good test loss. So that's why we only care about that at the moment. Then on the top right corner, we see the predicted classes for the elements in the test dataset. it seems like it should be test dataset. It's really interesting what I'm seeing there. The y is s, which is actually true, and y prim is t. Okay. Okay, I will look at that at the moment. By the way, the code is also on the Jamboard, so if you see, in the left bottom port, we see the projection in principal component analysis in 2 dimensions from the embeddings, from the layer one before the logits. If you want, you can also project the logits itself. And here we see the same for the classes in the test dataset. Because this is just like a dummy example with very small number of samples, we don't see any differences much here. But if we would try to train it on Google Colab, which we will do in a second, hopefully we will see something interesting. So before we do that, I need to check. I definitely need to check about something regarding the class samples, because this visual validation part shows something fishy there, because the S sample, so what would be nice to check as well is which samples are included in which class. So how to do that is following. So there is the train labels and test labels. So I want to print out, so I will drop maybe that line as well. So F train, so these will be the test labels, and then the train labels. So I want to double check that those are the correct ones. I will drop these lines as well. So this is really useful for checking. This is also on the Jamboard, slide number 9. So now I'm trying to run it again. We'll see which classes are included. And because we have the locked random seed, the random state 0, these should be always the same. So the last time I looked, the S, oh wait, it did not show. Okay, something is not right because it did not run. Okay, it did not run the correct code, sorry. So now I will try to run again the correct code. Okay, so here are the, so in the test set we have actually the letter S included. S and Y included. Okay, and I also have a problem here, sorry. I have a bug here. What is this bug? Ah, sorry, so here should be length of Y, or the batch size basically. So I will update this line as well and mark it so that you pay attention where there is a small bug in my code. So I will update the loss function. Okay, it's updating. Okay, in the Jamboard updated, right? So I will try to run it again. Actually, the output was actually as expected, so that's good. I don't need actually to run it again. The S is included class, and this is correct. So this is correct. Maybe the hack, which would be better, is to switch around test and train here, just for the classification example. So just for classification example. Because I want that matrix of the images presents something meaningful rather than just predict some classes which are not actually included in the training set. But of course, that might be also interesting. Okay, so what is this? Only. So I have some other bug maybe. So the loader train. Oh yeah, I have another bug. Oh, so bad. Anyways, I forgot that there is the summation. So mean So the mean should be around there. So already 2 bugs. As I do these codes live, so it sometimes happens that we get some bugs, but it's also quite, I think, useful to see the process of how to resolve the bugs when you have them yourselves. So it says that you cannot do the item function, or also you could not do the backwards function if you have a vector, not just one single scalar value with is in the tensor format. So in this case, the mean was missing around here, the average function. So before we got the loss for every sample, now we need loss for the whole batch. Try to run it again, and if it works fine, then I will try to run this on Google Colab as well, and I encourage you to also try this on Google Colab. So let me see. Okay, so now I have the V, so that is the actual class. Yeah, it seems good. Now it seems good. Definitely seems better. So I mean, the test and train should be switched around just because the way how I draw those last images, the last images then are picked from the train dataset now in this case. Otherwise, they are picked from the test dataset, which do not match the classes from the training dataset. So, but in the case of the contrastive loss, which we will implement just in a second after we do this, then in the case of the contrastive loss, then we will be able to actually classify also unknown samples, which is very cool. So if I try to now to run this on Google Colab, remember Google Colab, right? So this is the way how you can access GPU for free to train models. So not to do the crypto, otherwise they will ban you. So here there is the GPU in the settings of the runtime. So runtime, change runtime, GPU, right? So I drop this in here. What else? It might be, so I have 20 classes included. Okay, I need to also set debug to false. I set debug to true because some students might have GPU and maybe you don't want to run all of this stuff immediately from get-go. So I'll run it again. We'll see. I think it will download the dataset first, which will take some time. Okay, I don't know what's happening here. Okay, it's rotating. Okay, I don't see the dataset downloading. It seems like that something went wrong. Yep, definitely. Oh no, it started working. Okay, cool. Dataset is loading. Now, what's happening? Okay, well, meanwhile, I wait all of this stuff. I will open also the next task, basically. So this will be 1.3 implement contrastive loss and center of the mass classification. Using template from 1.2 task. So this part will be something that will be new. So far the things that we have done in the code is exactly the same things that we already did in the previous course, or some of the students have worked with themselves or with these kind of tasks for the classification of images, right? So now it's splitting the data set, collecting the samples. I definitely should have added that there is some limit of the samples, otherwise it takes too long. I would say that for you, I advise you to set here that the maximum length is, I don't know, like 1000. That would be probably better. Or like maybe 500, but maybe 1000 is good. So now it's trying to do something here. And for the contrastive task, contrastive loss Siamese networks, you see that it's called Siamese networks because you always have kind of pairs of the execution. For those tasks, for the next task, I encourage you to make a new copy of the file. So it would be really good if you can make a copy of the file and then run those. So let's see what happens. I have 16 classes in training dataset. Okay. The projection is not really awesome. It's just something there. Oh, we'll see. We'll see what happens for the next epochs. Okay, so when you're ready, so I would know that you're ready. Please submit the code in the Google Classroom, and then I will see that the first task is done. So what about the accuracies here? Right now, is still very low, 20%. I don't like the way how it is currently plotted. Maybe I should use different method for dimension reduction. But it seems right. It's just maybe too similar right now. Anyway, we'll see what happens. Also, one thing which is definitely not optimal is that the output of the model right now contains all of the classes, even though the actual number of classes in trained dataset is much smaller. Maybe that is one way how we could quickly improve the accuracy. But otherwise, like code-wise, this is correct basically. So I see that 3 people have submitted the task. It's very strange that there are not so many people in the Google Classroom, but anyways. Okay, still accuracy at 20%. The loss function is reducing. Okay, while this is running, maybe I can do a few improvements. So these are probably, these are like optional improvements. So what do we have here? So there's that part. So there's the axis for y indexes here. Y indexes selected from that part. That is correct. the model returns the probability distribution and the z vector. Okay, I guess the best improvement would be to try to encode the y probabilities into only in the train dataset. So I will add maybe a new slide on the Jamboard, which will be called on the slide number 10, which will be called improvements. Improvements. At the same time, I don't want to spend a huge amount of time here because we need to also implement actually the contrastive model itself. So let me see. In the on the on the Jamboard, it still got stuck about 20%, which is totally not cool. So here the improvements would be labels, train labels. So the code itself, it's okay, I think, I hope. So labels train. So this will be just for the labels train. So I will we can change that the distribution of the classes will not include other labels. So that is one improvement, but in order for this to work, there also need to be changed below few things. So then y index should also be changed. So what we could do here quickly, let me think. Maybe we could do something like this. So this will be then IDX. This will be mapping. So for in range of the length of y IDX, and then y IDX will be the actually then the train. So what was the situation? So where we have the train data set. So need the label as well, I guess. So this will be y label, which will be then the data set full labels by the index. And this should be then actually the item, I guess. Like that. I hope. Maybe you should also cast it to the integer. Then the y IDX. So what I'm doing is trying to not train the whole distribution, but just the distribution that is included in the train dataset. And here then we could use the train labels train index. Sorry, then we also need to check also this port. Oh no, I have few issues here. So IDX, y IDX item like that. Then index of this y label. Now we have proper y indexes, hopefully. And then if this works, I will drop this to Jamboard. Then the accuracy calculation also might be a problem now. MPY prim, so that will be correct. So we could also move the accuracy probably move the accuracy also to the train part only here. I just copied those two lines and moved it inside here. So now if I run it, I hope that there will not be a bug here, but it should converge much faster and better. Because now I'm not training it towards the full data distribution, but just the one. Okay, there's a problem. Okay, I got it. Got it. This part also probably should be moved inside here. Okay, by the way, these are optional parts. Maybe you should not do them, otherwise like it might be too confusing. It's just that I wanted to get some better results. So it seems to be working. So I wanted to get some better results for the visualization of the classification embeddings. Let me see. Okay, so far in the code that I ran on Jamboard, that was not giving satisfactory results. Try to run it again. Maybe there is some bug which I don't know. Okay, sorry, there should remove some few things. So there will be the debug should be false, and the maximum length of classes, let's keep it to 1000. Maybe I should, okay. So I will drop this part also to the Jamboard. If somebody wants to try out to get better results for classification, you could do it in this way. But now let's move on to the actually the contrastive loss part. So drop this to the Jamboard. If I will get at the end some nice pictures, I will also post them on Jamboard. I will show you. So yeah, I hope that now with those improvements it will work better. If not, don't worry, I will prepare some pictures later. So so that's so far. Then regarding the contrastive loss part. So here we will need to make some changes. So first of all, I will make a copy of the file. So save as. So this will be then not the classification, but contrastive loss 1.2 task. So where was it? Contrastive loss live. Okay, so this one. So here will be some fundamental changes. So first of all, that's why I said that a few things that I added were optional, because they are really not that important for contrastive loss here. So for contrastive loss here, what we'll do is, so what we could do is is remove the classifier part, so it's not that necessary. So there is the z vector here, and we could even not touch this part. So we will just not use the fully connected part here at all anymore. So we're going to use some other method here for calculating the accuracies and other parts. So so we're not going to use the y prim here anymore. Instead, we're going to use just the z vector. So let me just scroll a little bit. We can leave it as it is and delete some part of the code. So what we can delete is everything up till the loss function. So basically the only thing that changes here is the loss function. So really not so huge changes actually. So we need to find those pairs. Basically, we need to find all of the pairs in between each other, their distances, right? So let's see. So what would be the best way to do this? we have the y indexes, the class indexes, right? We have those. Okay, so let's write here small. So this will not be definitely optimal, but this will be just to explain how this pair finding works. So for I, and then there will be this yi in enumerate of the y indexes. So we will try to find the distances between those all of the samples in between each other. Definitely, I don't want to make it so that it's not too optimal here. Okay, let's write it a little bit different. So there will be okay, it's just to make it more different. So for in range of len of the so y indexes or whatever. So y indexes. This will be one part of the equation. Then there will be j. And the j will start from I plus 1, so it will not repeat the same combinations. So we're now going over all of the combinations of the samples. That is good. So these will be all of the combinations. So we can add here the losses. So these will be the all of the combinations of the losses for the loss. Of course, if you remember the contrastive loss equation, it is consisted of the two parts plus together, so it just means that we can split it out in this manner. So so that is one thing. Then we have those samples, so we can then select. So this will be then z anchor. Z anchor will be the zi, and actually we also probably need ya, which will be then the y index a, y index e, and then we could probably maybe we should write it okay, I just want to keep the same notation. Anyways, okay, so we can probably leave it as that for a moment. Okay, so if then ya equals the y index j. So if this is from the same class, definitely this code must be written better for production use, but here just let's make it as that. So then in that case, the z positive will be zj. So the class matches, the class is the same. And in case if it does not matches, then z negative will be the zj. Actually, maybe it would be even smarter to just like make it just make it in one large equation at the end. So let's do it in different ways. So here will be have all of the large z a. So these will be all of the anchor points for ZA, all of the anchor points for negative samples, all of the anchor points for positive samples. Negative samples, positive samples, and so on, right? So then we would add them. So here in this case is append z a and append z oh no. sorry for jumping around. So not z but d distances. So let's do the distances immediately here already. So this will be then the d positive distances. And here, of course, there should be quite easy ways how to calculate the distance. So, for example, one way would be using, so the distance could be L2 distance, probably. Okay, let's keep it the same dimensionality for the distances yet. So ZA minus ZP squared, right? And then negative distances, like that. ZN. Great. So hopefully it's so far so good. Then we need to calculate the loss function. Loss is then the so the first part is dp's. So there we could have actually this. It depends, like it depends on which part we actually want to calculate those mean values. We could calculate also here already. So torch mean, normally you would calculate it with multiple means, so that it would first be mean for each dimension and then mean for each of the samples. But let's try out first with just in a simple way. So this will be that part. Then the other part, the max function, is actually the same as ReLU, basically. The ReLU is basically exactly the same thing as max d negatives comma 0, right? So that is the same, except that there is also the margin term, right? So the margin term, let me see, so where was the equation in the slide number 7? So the margin term. So there will be the, let's say 0.2 minus, so this will be margin minus, this should be a hyperparameter up in the file. So with the dn's, and then also this could be mean. I'm doing separate means here because the number of negative or positive pairs could be different in between the runs, right? So this is hopefully fine. So this will be the loss function. So these are the positive ones, negative ones, except all of this loss function should be in the also in the train this part of the if statement. So that is the only difference here. So like that. Then the accuracy is something which will not work anymore. So the accuracy should be calculated using then the center of the mass of the clusters, or the clustering method. So the clustering method would mean that I would cluster the z vectors and then decide on which cluster the class belongs. But we will not do this now. So I will just keep it accuracy as 0, like that. We'll debug just to check that this is working so far. I understand that it might be confusing at the way how the code is formed around this loss function. If you have like more specific questions regarding the code, or you see some mistakes, you can try to ask them or post your code in GIST or some kind of bit bucket or something that I can share. So what is the, okay, the list, okay, there is a problem. Of course, these are lists. We need to convert lists to the actual tensors. So dp torch stack. So this will convert the list of tensors to just the one large matrix. So if we, before we had the, so what it is that if I had here the tensor z, something like that, then after the stack we get just that everything is tensor. So tensor z with the shape of the samples, comma z shape z size, basically, yeah. And this is like the stack. So this is what the stack does, right? So creates from the list the matrix form, and this is something that PyTorch then knows how to deal with. Otherwise, it does not. So dn. Try to run it again. Maybe also, I'm pretty sure that our model is very weak. There's very few parameters in the model. So this works, so that is good. At least it works in some capacity. The loss is reducing. And something is happening with the probability, with the z vectors. I don't know exactly what yet. I think also the model is very weak right now. For the homework, I will prepare a little bit better model. I will use some pre-trained model of the torch vision so that you can have better results, hopefully. So I definitely know that the model we just made, it'll probably have very few parameters. I will also show you how to check how many parameters you have for the model. Okay, so the train loss is reducing, at least for here for the test sample. So this part is hopefully right. I will drop this to the Jamboard. So the actually calculation of the contrastive loss. Normally in implementations in GitHub, you will never see this kind of implementation because usually you use torch NN functional pairwise distance. So there is a very useful function. So I will show you here on the Jamboard. So there is actually the pdist, cdist functions in CPy library and also in torch library. So to do this more efficiently, there are a few ways. One is this. Then another, I think it was also in the, okay, I need to make it larger, definitely. So, okay, like that. So the pairwise distance is one way how to make it better. Then another way is torch cdist and pdist functions. Okay, they are just in the base function. So in base function you have also torch cdist and torch pdist. So you can explore those functions as well. With these functions you can reduce those for loops so that you don't have any for loops basically. So, but if I would use them, maybe it would not be clear or what is happening. So here in the model itself doesn't look good at all. The accuracy is increasing, but it's increasing super slow. And so it's actually, there's a nice slope, but this is like only, again, 19%. And these doesn't look as well good. So my hypothesis is that the model right now has extremely low number of parameters, because if you remember, actually also LeCun, the same guy who invented these contrastive loss, he invented the convolutional neural networks to reduce the number of parameters that you need to learn. But in this case, I think we've gone too far, and the number of parameters for model is super low, most likely. So let me see what we could do to improve the situation. So what could be done here? We could use some kind of pre-trained model probably. Okay, let's try to use some kind of pre-trained model. So that was a good reminder how to do these models. So just to make this model powerful, what you then need to do is to like repeat these lines like, I don't know, like hundreds of times, make the automatic like for loops to make this like a lot more parameters, right? But the easiest path out of our problem here would be just to use some kind of pre-trained model, which in this case we can get from Torch Vision. By the way, also later on in this course, when we will work with the GANs, it's also often a problem that you make the model which don't have enough parameters, and then you don't get any good results. So ResNet, ResNet 18 will not have like huge like. It will not be the largest model, but it will still have much better number of parameters than what we had before. So this is a pre-trained model of the ResNet now. So we would use this, and then we use pre-trained true. Oh no, why it's hanging up? Okay, hope my computer will not freeze, because we still need to do a few things here. Oh no. Something is freezing up. Really hope that it will hold on. What else I can do? I can maybe close all of these guys. Okay, so this is then the encoder. encoder. In the encoder itself, if I remember correctly, there was something else there. ResNet, convolutions, fully connected at the end. Fully connected at the end is actually what we need here. Okay, so we can use that one as well. So this will be, let's call it not encoder, but just like, yeah, but this should be then an encoder actually. Okay, let's keep it as it is. Oh, I forgot also to remove softmax. Oh, okay, but we did not use the softmax. Okay, so it doesn't matter. So let's keep it as that. So this will be then the encoder encoder FC. So this is the last layer there. The last layer in that encoder, which will then have, oh no, sorry. So let's use the actually the encoder there. So FC. So this will be encoder FC. Will be torch linear, torch NN linear. In features will be the same as it was originally in pre-trained model, but out features will be our new like kind of dimensions what we like in the embedding model, right? So this will be that. So that is fine. Then we also need to extend a little bit those dimensions. So here the y prim will not exist anymore. So meanwhile, we can just define y prim, I think, as torch zeros, like z. For the homework, I will prepare a little bit better template for this. So this is, we're just not using the y prim. I don't want to change the code too much now. I just want to make the code very, very simple. So that is that part. So now we need also to extend the dimensions, because unfortunately the ResNet here is pre-trained. It is pre-trained on something which is at dimensionality of like 3, some width and height. So because I think it's pre-trained on ImageNet. So there is a function called extend. Okay, I see. Which version of Torch you are using? Oh, right. Sorry, I see in the chat that you don't have mesh. Don't worry. So please use Torch and then relu or leaky relu. So if you don't have the mesh function, which is in the last of the versions of the PyTorch, then really that is not something that should stop you. Just use something, some other loss function, some other activation function. So that is, then I will show you another way how to deal with the situation when the model is pre-trained on different type of inputs. So the one way is to expand dimensions to the larger size. So that would be just copying the pointers of the same input. So here what we could do is then expand. I think it will call like that, expand. So this will be -1 the batch size, 3 is the channels, then 28 by 28. So that part. I hope this will work, so I will add here a breakpoint. What I'm doing now is making the model much more stronger as before. The model that we did before was really weak, unfortunately. So okay, why it's downloading something here? Oh, okay, this is the okay, it works, seems good. So it downloaded the weights. So it seems good, and if I try to run it, so I will drop also this to the Jamboard most likely. So this is definitely not like a perfect version of a model. It's just something that would work much better than before. So I'm dropping this also to the Jamboard, slide number slide number 12. And on slide number 11, I will specifically write that this kind of loss function is the contrastive loss. So this is one version of it. Definitely next time we're gonna work with a little bit more optimized version. So I dropped that to the Jamboard, and it seems that it's working also here. Unfortunately, it's only very slow. So because the code is definitely not optimized, and this is why a little bit slow. So now I try to do the same code in the Jamboard, in the Google Colab. So remember, if you run this on Google Colab, then change the isDebug to false. I will include 500 samples per class. We'll see if something nicer appears out of this. So let me show you in the Jamboard. Okay, so it's collecting the data set. Y. So the false, there's a max of 500. So now it's training. Again, for these models, it would be possible just to change back from first start with training and then with testing. But it's really slow now. Okay, while it's churning up the numbers and hopefully getting some nicer pictures for us with a little bit more advanced model. Now, I just wanted to talk a little bit about the classification methods. So now if we have these Z embeddings, right, which are going in the right direction, making nice clusters, right, then we cannot really classify them using the like using just selecting the argmax, right? The argmax do not work here at all. So what is here? The NP index and the argmax, that is not working anymore. So instead, what we can do is try to see which type of classes are the closest to the clusters of the original yeah. So if we just cluster together all of these classes by the label, and then see to which center of the mass the Z vector is the closest one. That is one method. There is also other methods, like we could just cluster all of the elements and then see on which cluster there is the most overlap between the label, and then assume that that cluster is classified as that label. So, but let's try with the most simplest method. So the most simplest method would be following. So now here, if we're just looking at each batch, maybe that's not the optimal way how to look at it. It would be definitely much smarter to look at the whole dataset after each of the epochs. And we definitely can do that. Yeah, let's do that. So to calculate the accuracy, we would then go out of this loop. So there is this for loop of the batches, right? So I will move this part of the code out here. Also, we will define that accuracy is not actually a list, it's just defined as that. So that's one. Then what we could do is to calculate, to accumulate basically all of the Z vectors by their indexes. So here there is the class indexes, and here there are the Z vectors, right? So these are by the stages. So that is great. So these two things are all that we need, actually. So these two things is all that we need. So let's add here some comments. So calculate centers of the mass. So I will check the chat. Do we have some questions more? Okay, so cool. So the calculation of the centers of the mass. So okay, so there will be then. So what we can do here is to write. I'm not sharing the code. Thank you. So we're just. So what I'm doing is here I'm going after the for loop of the stage, right? So after this for loop, so we have the train test, then we have the batches, and then here after this loop, I want to calculate the accuracies based on the centers of the mass of each of the clusters that we just generated, right? So, and to do that, we use these two parameters, the Z's and Y's from the stage of the epochs, right? So we can maybe even write them out. NP, again, NP Z's. So this is this. and npys is this. So here we can write also classes by centers. I mean, centers by classes. Or labels, whatever. So, so this is this. Then we would go for y index in set of the y's. So we will go over only those y's which are included in this. Then we would select out those y's which are then presented in z's. So here what we can do is following. So matching y's is this thing, where this is equals the y index. Or actually what we could do even better is just selecting directly z's like that. So matching z's. I hope this works. So matching z's, and then the center, basically. Center will be then this average of all of those. So np mean of matching z's, axis 0, and this is then the center of that class. That class is y index, and this is its center. Again, I think like these changes we are always all the time doing, they're not like a huge amount of code. It's just like quite dense information of what we are actually doing there. So now it's just calculating these centers. I really hope that this works. I will debug it a little bit. And then the last part is just we need to calculate the accuracy based on the centers. Okay, the splitting part is very slow, unfortunately. The test part, okay, cool. Except there is something strange happening. So matching z's, so there is a 32-dimensional stuff, npjs. So this is that vector, which seems good. And npy is 60, and I see there's a multiple 60s there. And npz's is the shape. Something is not good. We'll fix that. Oh, npz's is a list, unfortunately. All right, got it. Got it. I forgot to convert them to the numpy arrays. So imp array, again, the same thing basically as in the stacks. So if I don't convert it to the correct type of data type, there's strange things start to happen. So np arrays should work better. Hopefully this part of the code is correct. I will assume that this works, and if not, then I will fix it later. So then the last part is then just to assign which class of index is it actually what it thinks it is. So on here we'll introduce a new variable which will be called y prim. Y prim index, which basically the same thing that would do the classification model would give us, right? But in this case, we will get it just by comparing the distances between all of these centers. So here, let's go over again the so not again not about these indexes, but we'll go over probably for z in np_z's. Cool. So we're going over all of the z's vectors. So now we could use I think pdist function, np pdist. I just want to calculate all of the distances to say, or I will maybe see this to the same output. No, cdist, definitely we're going to use cdist. We'll calculate all of the pairwise distances towards the center of the masses. So this will be cool. So okay, so here it's actually in the CPy library for the NumPy. In Torch, it's in the Torch, but in this one, it's a CPy. So cdist, CPy, spatial. Okay, sorry, I cannot include it in that manner. Okay, I should then include it up in the code. So I will drop here the line and then include it up in the code. So import this, or basically maybe we could even write it import cdist from CPy cdistance. This is just a useful function to calculate at once all of the distances towards the group of these centers, right? So I will include this function in top of the code. And from import from this thing, import cdist. Right, so now it's correct. Okay, good. This will not be a large piece of code, no worries. So again, you see up here we have how many lines? 1, 2, 3, 4, 5, 6, 7 lines here, and there will be also a few lines. Just so these will be then the distances to the centers. So this to centers, cdist, and here we need to use so dimensions which should match along one of the axes. So by default, by the way, this will be metric will be Euclidean. So so here, let's see. So NP array of the centers values with regards to interesting. I could in fact do this at once. Usually I do this for the batches, that's why I was a little bit confused. But okay, let's do it in this manner here as well. So z, but then z must be expanded a little bit. So z expand dims, or np expand dims, and I hope that the axis at which I should expand it is either 0 or -1. So metric will be Euclidean. Basically all L2 distance. Yep, and here I will add a breakpoint just to double check that everything is working as expected. So right now what I'm doing, I'm calculating the distances between each of the z samples and all of the pre-computed centers of the masses. It could be done also without that for loop but let's keep it as it is. Are you saying NPZs but writing NPYs? Okay, thank you. I'm checking. Oh no, you don't see the code again. Oh no, you see the code. Okay, cool. Okay, no worries. I will answer the question. Look at, maybe there is some bug there. So, okay, it didn't like that the distance, so I guess I need to expand it along -1. That was what I was worried about. Okay, let me check what you asked in the chat. NPZs, but writing for in NPYs. Yes, you're right. Thank you. That is one of the reasons probably this didn't work. So let me run it again. Yes, you are absolutely right. I want to go over every z vector that we just produced with our model, and I want to see how far this z vector is of the center of the class of the similar z vectors. So if I have those letters A's, then they are all clustered together, and their center of the mass will determine, like if this sample is the closest to that center of the mass, that is the letter A. If some other sample is closer there, then that will also be classified as letter A, but even though it might not be that class. So there is still some problem. Very strange. So what about what is here happening? So the XA, let me check. So what is here happening? Values. Okay, this seems strange. Very strange. Dictionary values. Okay, I need to convert them to the list, I guess. List. Yeah, now it seems better. So I have two classes there. Yeah, I need to convert, unfortunately, to the list. So if there is a spaghetti starts happening, then I will just split it in multiple lines, unfortunately. So, and this should be converted to list. Thank you for following the code. You helped me out by finding out that small bug with regards that here was wrong variable. Okay, is it working? What's happening? Okay, testing. Okay, cool. Yeah, it actually worked, so that's great. Maybe even I didn't have to expand it because now I have kind of strange stuff happening here. So I have two distances, and so probably need to squeeze them. Squeeze. And then I will select the minimal distance from these, and this will be actually the y index. So y prim, and let's call them also, yeah, so I don't know, like y prim index, okay, anyways, so y prim index each. This will be then the NP argument. So the smallest distance from the distances that we just calculated. So the smallest distance of these things will actually be our designated class. So, and if I have my designated class, I can append it. Append to this guy. And finally, I can calculate the accuracy then. Except I also need then to convert this to the numpy probably, because again, then strange things might happen. And P array of this. So using the Z embeddings, we just calculated kind of the accuracies based on how close they are to the clusters. So yeah, y indexes equals with the y's, and p y's. and then multiplied by 1, and then this is a mean value, np mean, like that. Okay. Yep, so this should be fine. Hopefully I will run it. If there's no bugs, then this will be done. And finally, then you just need to train it and see, get some nice pictures, which we unfortunately so far do not get. We might have some bug there. It's a possibility, unfortunately. But if I have bug, then I will just fix it, and for the homework you will have a nicer template. So for the homework I will make a template so that you will have some additional tasks to improve the contrastive loss. And next week we will discuss about the sampling methods as well. So, and then definitely we should get some nicer pictures, because this is very naive, very vanilla type of contrastive loss, where a lot of things might not work as well. So let me see if there's no bugs. Yeah, there is no bugs so far. It seems to be working. Oh no, except we have something here, the float. So doesn't like some kind of float. Maybe we should add float here. It's too high accuracy to write in the actually where it is. So the len metrics. Okay, this is the len metrics. Oh no, it's not the high accuracy. It's just that we want it to be something like that probably. Value len, yes. I think hopefully now it will work. Yes. So we'll run it again. Run it again and add this part of the Jamboard. Really not a huge number of lines, really small number of lines to be added just to make calculation using the centers of the mass. Hopefully, at least in the intuitive manner, you understand what this code does. So it calculates the classification of the class based on how close this is to the center of the mass. So let me drop it down. And I will try to illustrate this last point before we end today. So the way how we classify these classes is by, for example, if we have here one class, right, with some samples, and then we have the green class with some samples, right? It's really not so visible, right? But still, and then there is one green sample here, right? So what we're going to do is we will calculate the centers of the mass for each of the classes. So for the red classes, the center of the mass is here, right? For the green classes, its center of the mass is here, right? So then the next thing is we look at this sample. So is this sample belonging to this class or to this class? So the distance is shorter to the red class, and it says that this sample belongs to red class. But in case of, so this is wrong sample, right? But in case of the red sample here, this is shorter distance and this is longer distance, so the red one is correct. So the red one is correct, and the Y one is not correct, right? The green is not correct based on the distances of the centers of the mass of the of these basically clusters, right? So I hope this is clear. I really hope that this is clear. The only matter now is that it would be great if it actually would work properly on the Google Colab. Okay, something crashed. I guess the same error as before. Yes, this one. So where was it? Where is the error here? Yes, yes, yes. So even if I don't get now really nice pictures, then I will prepare the template for the homework so that would work. At the second, I don't really 100% sure. Where do I have bug? Oh no, I see the bug. Oh no, nobody also noticed it, but it's nice. At least now I have something, we will have something nice to see. So the bug is in this line. I will also add this to the Jamboard so that you can fix it. So unfortunately, I scattered the same dimension twice. Here you should be endpoints -1, -2, not -1, -1. So that was my bug. That's why these lines are in symmetrical like that. So here there should be -2, -2. So this is the bug for visualization. So let me then also show you what I mean. So here in these lines, these should be changed. This is my bug, unfortunately. So why this stuff opened? Okay, so this line, again, repeat, there is a small bug. It's just that I copied those lines and I did not notice that here the index for the Z is wrong. I will definitely update the template for those of you who are gonna do this work later. And for the homework also update the template. So, and the good news is that hopefully in the last minutes we will get at least some interesting pictures. So here there is a bug on the slide number 14. I'm adding here a bug. So bug in visualization. Okay, so please fix that. And now if I try to run it here, -2 seems good. Yeah, that I should have noticed sooner. It's really not a huge bug. So, but okay, now it's running. I suspect that the visual output should be much more interesting now. Okay, the training is a bit slow here. And what about like if I run this locally, even on those few samples, I should get something more visually interesting. Okay, it's running also very slow here. Basically, the code that is for the, as you already saw, that we can use cdist function, and if we would use cdist function inside the training loop using torch, then this would work so much more faster. You definitely know that you are smart enough to rewrite these for loops using the cdist function, which it compares automatically all of those combinations, and that would be much better. But now we stick what we have. So just wanted to end this session with a few pictures. So yeah, you see that now the classes are distributed like more in the manner as I was describing them as a clusters. There was just a bug there with the projections there. So that's one. Also, I really hope that we will see something properly trained on the Jamboard here. And yeah, so maybe we could wait a few, like I don't know, like minute or so. What is the estimate here? 40 seconds. So if you can wait 40 seconds, then we can end for today's work. Let's see if we can get some nice picture after the first epoch using the larger data set. Okay, and then for homework, you will have, again, a bit nicer template, and you will also have the task to implement extension to the loss function. Basically, you will need to combine the classification with the contrastive loss, and you also will have to try to classify classes not using the center of the mass, but using the k-means clustering. So, okay, the results, like after the first epoch, they're not like spectacular, but basically everything works, and visually now it looks much better. So till the next time, we'll definitely get nicer pictures so to share with, and we'll also have quite interesting homework. We'll try to make it as simple as possible. I mean, like, I will try to give you as much as code as possible, and you will need to add only a few things which would help you to understand how this works. This is it for today. I hope this is really interesting, and